Before we begin the momentum, I just want to introduce one concept that might seem a little bit out of the blue, and that's central forces. So let's imagine for a moment that a system is rotating about a fixed point. So that would just be like an asteroid spinning in space, or like a person holding onto a bar on a merry-go-round, whatever. But it's a rigid body, or rotating rather. So this is the kind of thing that we've dealt with a lot, but the picture is just, you have some lumpy thing, you have your pivot point, and then this whole thing is just spinning around it. Fine. So in this picture, if we were to look at just a single chunk of material and then examine the forces and the acceleration and the motion of that object, or that little chunk, we would find that that chunk is moving in a circle, right? And so when we know that whenever a chunk of an object is, or whenever anything is moving in a circle, whether it's a chunk of an object or it's its own thing, we know that object will experience acceleration. In particular, it will have centripetal acceleration. And that's just because anytime an object moves in a circle, in order to keep its velocity changing, you have to have some acceleration, which bends it towards the center, right? So that means that every particle in the system experiences acceleration. Every chunk, except perhaps the one at the center. And if every particle in this system has an acceleration, that means that every particle has a net force on it. And maybe that net force is external, maybe that net force is internal, maybe it's the other particles grabbing it and pulling it along, whatever. But then you might ask, okay, well, if every single chunk of material has some force on it, maybe this way and then that way or whatever, how could it be at all possible that an object that's just spinning, not changing its rotational rate, just spinning, how could it be that the net torque on that object is 0? Because we know if an object is just freely spinning in space, the net torque has to be 0, right? But how could that be possible if every single point, if there's so many forces involved? And so the key here, Ollie, get down from there. He's trying to get into the rice bag. The key here is that for circular motion, the acceleration vector points towards the center. Ollie, what are you doing? Get off the rice. Sorry, I don't know why he's doing that. Well, he's being annoying. He's trying to like climb on top of the rice bag. You guys have met him before. Right, so for circular motion, the acceleration of that object points towards the center. So perhaps this arrow was wrong. Maybe it would be this arrow. Okay, it points towards the center. And so that means that the force vector points towards the center. And so if we draw a vector from the pivot point to the location where the force is applied, this vector from that is to say, the force vector points in the opposite direction. Now he's next to the printer. Force points in the opposite direction of the displacement vector from the pivot. So the force vector is in fact parallel, really it's anti-parallel, to the vector r. R points from the pivot point to the location of the object, or the location of the particle. And that automatically tells us that the net torque on that object, on that particular particle, which is r cross f, has to be equal to 0, because the cross product of two vectors that are parallel or anti-parallel to each other is 0. Right, so we can actually talk about what this kind of phenomenon in general. Here, we had a force that points towards the center of the pivot, or towards the pivot point. And so we saw that no torque arose from that force, whatever that force might be. And so we can actually define a central force. So a central force is a force which can act on many objects that is directed hard to say, directed directly toward or directly away from a single point in space. So in the example given, whatever force is present on all of these particles would be an example of a central force, because the force on all of them always points towards the center. And that force can act on a whole bunch of different particles. In this case, it acts on every particle. Or it could just act on one, like in the case of like gravitational force. It just acts on, like, if you just have like an atom in space, it just acts on the one atom, right? The point is the force points towards a single place in space. And so in general, central forces don't exert torques or they don't exert torques relative to the central point. Because the force always points towards the central point, and the vector r points from the pivot point, the central point, to the location of the object, r cross f is always 0 for these central forces. And so that is to say, angular momentum around the central reference point is always conserved, because from the impulse momentum theorem, the rotational impulse momentum theorem, if there are no external torques, or if there's no torques at all, then angular momentum is conserved. And we're going to look at angular momentum conservation today. But I just wanted to introduce this notion of a central force, because central forces are relatively common. Think gravity is an example of a central force. Any force causing centripetal acceleration is a central force, and so on. So the fact that those do not produce torque and hence conserve angular momentum, very handy. So let's talk about angular momentum conservation. And that's what we're going to spend all day today on. That's not Hastings conservation. So just as a quick reminder, if you have a system and the external forces on that system sum to 0, like the net external force is 0, then the translational momentum is conserved, written as delta P Cm equals 0. This is the change in the center of mass momentum of the system is 0, i.e. the final is the same as the initial. And so we can use this property to solve problems that have complicated internal forces. Problems like collisions where there's bouncing and rubbing and all sorts of complicated things. We can just ignore what's happening internally because of Newton's third law. We can just ignore that and only look at the external forces. And if there are no external forces, then the problem becomes much, much easier. Similarly, we can do the exact same thing for rotational motion. So from the rotational angular momentum theorem, rotational impulse momentum theorem, we have that the net torque times delta T is equal to the change in angular momentum. So this is external torque, by the way. If the external torque on a system is 0, then the angular momentum of that system, and by the way, all of this is relative to the same reference point. So if the external torque is 0 relative to a reference point, then the angular momentum relative to that reference point is conserved. That's built into these equations. But the point is we can use angular momentum if we know, say, the initial angular momentum to find the final angular momentum, even if something complicated is happening internal to the system, so long as there are no external torques. And so again, just like in the translational momentum case, where we can use this to solve complicated problems like collisions, we can do the same thing here. We can solve even more complicated problems that involve rotational collisions and so on. So let's look at a simple example of a rotational collision. So what we're going to do is we're going to suppose that we have a spinning plate, just like a disk that's rotating really fast. And it's dropped onto a stationary plate. Now, the stationary plate is sitting on a frictionless table, but both the spinning plate and the stationary plate would have friction relative to each other. So when they're sliding, there would be friction between them. So actually, I'll just draw a picture rather than writing that out. So we have a spinning plate spinning with, say, some speed omega. And then we have, sitting on a table, we have an identical plate, not spinning at all, and the spinning plate is dropped onto the stationary plate. So we know that the spinning plate is initially going to be rotating. Eventually, it'll come into contact with the stationary plate. And at that point, there will be a friction force. The stationary plate is stationary, the spinning plate is spinning, and they're in contact. So there will be a friction force. The stationary plate will apply a friction force on the spinning plate, which will cause it to slow down, whereas the spinning plate will apply a frictional force on the stationary plate, which will cause it to speed up. The way to think about this is, remember the book example where you had two books sliding, you had one book stationary, one book was speeding, and then the top books slid on top of the bottom book, and they ended up moving together, even though the top book slowed down, and the bottom book sped up. This is the same thing, just the rotational equivalent. And so what ends up happening is you end up with, at the end of the day, after all is said and done, you end up with two spinning plates in contact with each other, spinning at the same rate. And we can use angular momentum conservation to understand what that rate is. So let's look at this example. Let's say that the bottom plate has radius r. And by the way, we're going to look at a more complicated example than just plates are identical, rather than just the situation where the plates are identical, because when the plates are identical, the final angular speed is just half. We're going to look at a slightly more complicated example. So the bottom plate will have radius r. The top plate will have radius r/2. So the top plate is slightly smaller. We're going to assume that they're made of the same stuff. And we're going to assume that the initial angular speed of the top plate is omega naught. Just giving some variables to these things. So then we can ask the question, how fast are they spinning after the plates come together? i.e., what is the final angular speed? So in this case, about the central axis, the axis that they both share, you drop the spinning plate on top of the, like in the middle of the stationary plate, the net torque is 0, right? There's really only one force. That force would be gravity, maybe. I suppose that there would also be a normal force, but those point up and down. In particular, those point up and down through the center, through the central axis, so those are not going to do any torque. So we can have that the external torque here is 0, for where external means outside of the two-plate system. So we have that the total angular momentum of the system is conserved. So we can work with that. This is about the central axis. Yeah, we're assuming that the table's frictionless. It's just something to keep it up. So what is the initial angular momentum of the system? By the way, I'm dropping vectors because this is effectively a one-dimensional problem. The initial angular momentum is the moment of inertia of the top plate times omega, what did I call it? Omega naught, plus the moment of inertia of the bottom plate times 0, because it's not spinning, right? The final angular momentum, on the other hand, would be, well, they come together and they're spinning at the same rate. So it would just be the sum of the moments of inertia times the final angular speed. You could distribute that to see that it's the angular momentum of the top one plus the angular momentum of the bottom one. And so because the angular momentum is conserved, we have that the initial angular momentum has to equal the final angular momentum, and hence solving that for the final angular speed, we get that this is I top divided by I top plus I bottom times omega naught. Okay, great. Now we're not quite done because we have enough information that we can actually find out what I top and I bottom are, at least in terms of the variables given, like the mass and the radius and so on. So we're going to assume that the disks are both uniform in density, meaning that they're not lumpy, and that they have the same density, like they're made of the same material. Then, in that case, the mass of the lighter one should be 1/4 the mass of the heavier one. Sorry, the mass of the smaller one should be 1/4 the mass of the bottom one, of the bigger one. And the reason for that is just that, think about how the area of a disk scales with radius. If you double the radius, you quadruple the area. And because they're made of the same material and have the same density, that means that you have a quarter of the amount of material in the top disk as you do in the bottom disk. So the mass would be a quarter as well. So we can work out what the moment of inertia of the top disk is. It would be 1/2. Again, we're assuming it's uniform. So it'd be 1/2 times a quarter times the bottom mass times r over 2 squared. That's supposed to be a 2. And then and we can expand this. We just get that this is 1 over 32 times the mass of the bottom disk times r squared. And the moment of inertia of the bottom disk is just 1/2 times the mass of the bottom disk times r squared. Okay. So now we can actually just plug these both in. And we find that the final angular speed is 1/17 the initial angular speed, which is actually really, really low, kind of surprisingly. But maybe it's not surprising because the top disk, while it's spinning much, much faster, 17 times faster than it was after it came into collision, effectively has a lot less mass. Not only is it smaller, so the mass is closer to the center, it also just has less mass total. So it takes a lot less effort to spin up the smaller disk than it does to spin up the heavier disk. So we know that this kind of collision is the kind of collision where two things come together and end up at the same speed. So this would be like an inelastic collision, a totally inelastic collision, actually, because they end up with the same speed. It's just a totally inelastic rotational collision. Why is it again that the top has a quarter of the mass of the bottom? Just because the area scales as the radius squared. So if you double the radius, you quadruple the area. And so if one disk has 4 times the area of another disk, then it's going to have 4 times the mass. So it's a totally inelastic collision. It's just rotational. And so we can actually ask the question, how much energy is lost to thermal energy? Or rather, how much kinetic energy is converted to thermal energy? And we can do that just by comparing the final kinetic energy to the initial kinetic energy relatively easily. And so the initial kinetic energy, well, we can just compute. It's 1/2 times 1 over 32. It's 1/2 I omega squared, remember. I is 1 over 32 times the mass of the bottom disk times the radius squared times omega naught squared. The final kinetic energy is just the sum of the kinetic energies of the two disks. So 1/2 times, again, 1 over 32 m bottom squared, or m bottom r squared, omega f squared, plus 1 over 2, or 1/2 times 1/2 m bottom r squared. I'm just doing these calculations so you don't have to do them. And after simplifying all of these, substituting in, so we can substitute in the 1 over 17 into omega f, and then we can do this calculation. We end up with that the final kinetic energy is 1 over 1088 m bottom times r squared omega naught squared. Some random number. And so we can check the ratio of the final kinetic energy to the initial kinetic energy is 1 over 17, which is actually kind of nice that it shows up to be the same value. That won't always happen, but it does happen in this case. And so this is to say that the final kinetic energy only has about 6% of the initial kinetic energy, meaning that almost all of the kinetic energy was lost to thermal energy, which is perhaps not surprising. The top disk slows down a lot. It slows down by a factor of 17. And we know that kinetic energy goes as 1 over, or goes as speed squared. So if you reduce the speed by, say, a factor of 4, you reduce the kinetic energy by a factor of 16. Now that's compensated by the fact that the bottom disk speeds up a little bit, but it doesn't speed up very much because it only speeds up to, 1/17 of the original angular speed. So the fact that so much energy is dissipated, it just is. So we're ignoring, we're ignoring the potential energy here. This is just ignoring gravity, ignoring any of that. Just imagine you have one disk and then another disk coming down on top of it. It's not necessarily falling. In principle, you would have to deal with potential energy to gravity as well, but we're not worrying about that here. Just like how we don't worry about the gravitational force often when we're worried about translational collisions. Yes, no, so it did lose 16/17 of its kinetic energy. It did. the 1/1088 resulting from the kinetic, yeah, the final kinetic, yeah. All you do is you just plug in the 1/17 into omega sub f, and then you just simplify. Right. Okay, so that's one type of collision. And it turns out that getting like totally elastic rotational collisions, yeah, it's just due to the friction. It turns out that getting elastic rotational collisions is a little bit harder to like come up with examples for, just because they're not really bouncing off each other. And so we're not going to do an example of an elastic rotational collision. Instead, we're going to talk about something that actually doesn't have an analog in the translational case. So we're going to talk about angular momentum conservation as it applies to changing rotational inertia. So I will be right back. It is demo time. I'm going to go get my lovely spouse. Hopefully you can see me over here. Can you see my foot? Okay, that's good enough. All right, so here's a spinny chair, office chair. What I'm going to do is I'm going to have these two weights, they're like 5 pounds each. Notice that my rotational inertia will be greater when the mass is far from the axis of rotation than it is when it's closer. So we're going to see what happens when I start off with some angular momentum with my rotational inertia being large because the mass is far from my center of rotation. Then I'm not going to do anything. There will be no torques, there will be no collision, nothing. All I'm going to do is I'm going to change my rotational inertia by bringing these closer to me. We'll see what happens to my angular velocity as my rotational inertia changes. So I'm going to have my lovely wife spin me up. This might be dangerous. We'll see what happens. Spin me up as fast as you can and stay far away because this will hurt. All right, so it's out. I'm going to bring this in. Oh boy. So I'm spinning much faster now. Putting it out, I slow down significantly. You can bring it in again, and I speed up. And I can just keep doing this. It's a very strange feeling, I'll give you that much. But what we saw, or hopefully what you saw, is that when my hands were out, I was spinning much more slowly. When I brought them in, I spun a lot faster. We'll see how that actually pans out in a simpler example that we will do in just a moment. I'm going to make my way safely back to the desk because I'm really dizzy. So we're going to explain why that happens with a simple example. All right. Oh boy. If you looked at my eyes right now, they'd be going like this, because that's what happens when you're dizzy. Yeah, like a figure skater. That's precisely what it's like. My spouse is not a physics person. She's actually a law person. Her name is Vivian. Right. So that is the yes. So we could analyze that situation that we just did. We could see what happens, and it would be doable. It's just kind of complicated because notice that my arms don't pull in straight back. There's some other things changing, like my elbows are moving places, and I have some moment of inertia that's also changing external to the actual weights. So we're going to instead, we're just going to analyze a very similar but simpler example. No, the cat would have thrown up, and he throws up enough as it is. So let's look at a simpler example. So in this simple example, we're going to have a child standing on the edge of a merry-go-round. Merry-go-round, and the merry-go-round will forever now be abbreviated MGR. And the merry-go-round is spinning while the child is standing on the edge. Maybe he's holding on, so it's just spinning, going around at some speed, and then some speed omega. It's rotating at that speed omega. And then the child walks towards the center while it's still spinning. Now, you can see how this is an analog of the demo I just did. The child plays the roles of the weights being drawn in, the child coming closer to the axis of rotation. And so you would expect, hopefully you would expect, that the angular momentum, while remaining fixed, the angular velocity will increase because the moment of inertia is decreasing. So there are no external torques, just like how there are no external torques once I started spinning. And so the angular momentum is conserved, as mentioned. And just so that we can give variables to this, we're going to let m be the mass of the merry-go-round. The merry-go-round, we're going to let little m be the mass of the child. And r is the mass of the merry-go-round. So, sorry, r is the radius of the merry-go-round. So now we can write out what the initial and final angular momentum are, just in terms of omega, omega naught, and omega f. Let's actually call it omega I, so it corresponds to omega f. Right, so the initial angular momentum of the system would be, well, it's the angular momentum of the child, who we're going to treat like a point mass, plus the angular momentum of the merry-go-round. So the angular momentum of the child would be the distance the child is from the center, squared times the mass, that's the moment of inertia, so it's mr squared, times the angular velocity, plus, so we're doing I omega for both the child and for the merry-go-round. So the I for the merry-go-round, assuming it's just a flat disk, uniform disk and all of that, it would be 1/2 times mr squared times omega I. So we can rewrite this as mr squared plus 1/2 mr squared times omega I. Okay. The final angular momentum, well, once the child reaches the center of the merry-go-round, they no longer have any moment of inertia. So they don't contribute to the merry-go-round's angular momentum. Even if they're spinning, we're treating them as a point, so they would have no angular momentum. So and that's just because the r becomes 0. So the final angular momentum would just be 1/2 mr squared times the final angular velocity. So the fact that angular momentum is conserved lets us just solve for the final angular velocity. This would imply, you can set up the equation yourself, but it just gives us that the final angular velocity, or angular speed rather, is 1 plus 2 little m over capital M times the initial angular speed. Wouldn't we have to? No. And that's just because, so imagine that, yeah, no. So the moment of inertia of the spinning of the merry-go-round doesn't change. So that's this term. The moment of inertia of the child, though, goes from mr squared to 0. So the angular momentum of the child, once the child is in the middle, is 0. And the angular momentum of the merry-go-round is just whatever it is. So one thing to note from this example, assuming that all of the masses are positive, which of course they are, this is bigger than the angular momentum, or this is bigger than the angular speed of the child on the outside. This is to say, when the child walks in, the merry-go-round speeds up. And that's just the same as how I sped up once I brought the weights in. And it's bigger by, this factor, twice the mass divided by the total mass of the system. And that's just specific to this scenario. In my case, I would have had 2 masses brought in, so maybe it would have been 4 times the ratio of the masses or whatever it is. So now, okay, so that's fine. That's just what the answer is. That's what the final speed is. But now something tricky happens. So let's compare the kinetic energies of the initial and final situations. So just like for translational motion, it's because kinetic energy is 1/2. Sorry, that shouldn't be squared. You're right. You're right. Yeah. Yes. So just like how for translational motion, we can write the translational kinetic energy as p squared over 2m, we can do the same for rotational kinetic energy. Rotational kinetic energy can be written as L squared over 2I. That's just true. You derive it using the same type of algebra that we did. So let's compare the initial and the final kinetic energies by comparing the initial and final momenta or moments of inertia, because their angular momenta are the same by angular momentum conservation. So if the moments of inertia change, then the kinetic energies will change. So initially, the moment of inertia of the system is mr squared plus 1/2 capital M r squared, because moments of inertia just add. After the child walks to the center, the moment of inertia of the system is just 1/2 mr squared. So what we see is that the moment of inertia of the system decreases as the child walks towards the center. And because the moment of inertia decreases, that means that the kinetic energy increases, which is to say that the initial kinetic energy when the child is on the edge is smaller than the final kinetic energy when the child is in the middle. And that's just because the initial moment of inertia is bigger than the final moment of inertia. So this should be baffling, because what it sounds like is the system just got energy out of nowhere, right? You just have a child walk towards the center, and now there's just all of a sudden more kinetic energy. And that is strange. But the way that we can understand that is by examining the internal forces. So let's consider the internal forces in the system, internal to the merry-go-round child system. So when the child walks towards the center of the merry-go-round, there's always a force acting on the child, right? So what is that force? Well, the only force that's really present, because the feet aren't slipping on the ground, would be static friction. And when the child is stationary on the edge of the merry-go-round, there is a force on the child keeping the child moving in a circle, right? That would be static friction. The static friction force points towards the center because it provides the centripetal acceleration, and it keeps the child moving in a circle. When the child walks towards the center, two things are happening. They're still moving in a circle, but they're also now slowing down. Like their translational velocity is, or the translational speed is changing. So it points both towards the center because they're still moving in a circle, and tangent to the circle. I'll draw a picture in a minute. And the reason it acts tangent to the circle is because when the child is on the edge of the merry-go-round, they're spinning fastest. As they get close, and not angular speed, I mean their translational speed is fastest, because translational speed is r times omega. As they get closer, their translational speed decreases because their radius is decreasing. Even though the omega is increasing, it turns out the radius is decreasing faster. And so they are like their straight line motion, their straight line speed, translational speed, is decreasing as they get closer to the center. And so in order for that to happen, there has to be a force acting on them. And that's basically the friction of the merry-go-round pushing on their shoes in the other direction of rotation. So the picture is something like this. So you have your merry-go-round, this is viewed from above. You have your child perhaps at this point, so the whole thing is spinning this way. The child might have some speed, vi. As they get closer to the center, and that's because they're tracing out this circle, by the way. As they get closer to the center, they still make one revolution in the same amount of time, or a slightly different amount of time. But now the circle is smaller, so their speed will be smaller. And so in order to lower that speed, they must have had, in the in-between time, they must have had they still have the force that's pointing to the center, because they're still moving in a circular motion, but they also have a force that's pointing slightly back. That's reducing centripetal forces. No. And remember to ask public questions, because so everybody can see. So there has to be a force that's pointing both back to lower their speed and towards the center to keep them moving in a circle. So we see that the force is actually, part of the force anyway, is actually in the same direction, or rather the opposite direction of motion. When the force is just perpendicular, there's no work done, because the force dotted into the path length, the vector that is tangent to the circle, like these little paths, when the force points towards the center, that path length, or that dot product is 0, so there's no work done. On the other hand, once the child starts moving in, because they're slowing down, they have to have a component of the force that points in the opposite direction. So there will be work done. And similarly, we can then answer the question as to why the merry-go-round speeds up. And the merry-go-round speeds up because from Newton's third law, the merry-go-round is applying a static frictional force downwards or backwards here on the child. So the child, from Newton's third law, applies a forward static frictional force, speeding up the merry-go-round. Why wouldn't there be work done in the initial system? So when the child's just standing there and not moving inwards, there's no work done because the path is this way. The path is the path that the child takes is in the direction of the velocity vector, but the force points towards the center. So F dot dl in that case is 0. So the work done, remember work is the integral of F dot dl, the work done would be 0. It's once the child starts moving inwards that they have this static frictional force slowing them down that the work stops being 0. And so what's happening here is you have some sort of internal work, and that internal work really is a result of basically chemicals in the child's bodies being taking their potential energy and converting it to mechanical energy and then thermal energy by way of static frictional force. Effectively, that's what's happening. But let's simplify the system even more. So let's consider an even simpler example. So if the mass of the merry-go-round is 0 and the child only walks halfway down, then we can actually calculate. So I'm using a simpler example just to illustrate the point, not because we can't do it the other way. So, and using angular momentum conservation, we would have that the initial angular momentum, so in this case, the spinning merry-go-round has no angular momentum because it has 0 mass. So it's just the child spinning. So the initial angular momentum would be mr squared omega naught, spinning at some initial speed omega naught. The final angular momentum would just be the child again. But this time their distance to the center is half as far away as they were. So in this case, it'd be mr/2 squared omega f. So putting these two together, we find that this child's rate of rotation, the rate at which it goes around the merry-go-round, and this would be the speed that the merry-go-round also rotates at, would just be 4 times the initial angular speed. So now let's look at the change in kinetic energy of the system. So that's just the final kinetic energy minus the initial kinetic energy, which would just be L squared over 2IF, final moment of inertia, minus L squared over 2II, initial moment of inertia. And we know what the moments of inertia are. So this is just L squared over 2 times mr squared over 4, minus L squared over 2 times mr squared. And so this is just 3/2 L squared over mr squared. We know what the angular momentum is. It's just this. It's conserved. So we can plug that in, and we get that this is 3/2 mr squared. This is the change in rotational kinetic energy, is 3/2 mr squared omega naught squared. So this is to say the final kinetic energy is higher than the initial kinetic energy by this much. So now we can check, using our understanding of this force, the static frictional force that slows down the child, like in this example above, we can check that's how much work is done. So now we have some work to do, no pun intended, because we want to check that the work done is equal to the change in kinetic energy. That would be a good thing. So this is going to take some work. So by the way, I lied a little bit. So it turns out that when the child is actively moving inwards, should L final be? So I just put L because it's conserved. The initial and final angular momentum are the same. Right. So I lied a little bit. which is to say when the child's actually moving, they're not moving in a circle anymore. So the static frictional force, doesn't actually necessarily point towards the center. In fact, the static frictional force just points in the direction that they're moving, i.e., if you viewed this from a non-inertial reference frame, which gets confusing, and we're not going to talk about that, but just bear with me. From the perspective of the child, the static frictional force only points towards the center, and they're moving towards the center. That's from the perspective of the child, right? They're not going in a circle, they're just moving towards the center, and there's a force, static frictional force moving towards the center. And really, that static frictional force would be the centrifugal force, or rather, it would be the cause of the centrifugal force. Anyway, this is just all to say that we can actually figure out what force and in what direction relative to the direction of motion the child is moving in. So if the child was not moving, relative to the merry-go-round, to the MGR, then the acceleration that the child feels would just be, or rather the net force on the child would be determined by the centripetal acceleration. And that force is the static frictional force. Which is to say that the magnitude of the static friction, when the child's just not moving towards the center, they're just sitting on the edge of the merry-go-round, this would just be m times AC, right? So now imagine what would happen if the static frictional force were somehow just a teensy bit bigger than that. Well, so they're moving around, the static frictional force points towards the center, and that's keeping them precisely moving in this circle. But if the static frictional force were just a little bit bigger, now they have to be moving in a smaller circle. And the reason for that is because they'd be turning faster than their bigger circle could account for. And that makes sense because if they're walking towards the center, then you would expect there's some force pointing towards the center. So in that case, if the static friction force were slightly larger, if there were in fact any amount greater than the mass times the centripetal acceleration, then the child would move inward. So now I'm just going to do a calculus thing, and we're going to take the limit at the end of the day. So we're going to let epsilon just be some positive number that's small. It's just some positive number that has units. It's just some really tiny number. It's whatever. So the static friction force So we're going to let the static friction force be MAC plus epsilon. So it's a little tiny bit bigger than the actual force required to just move in a circle. So because the static friction force is bigger than the mass times the centripetal acceleration, the child will very, very slowly walk towards the center. It'll be slow, really slow, because epsilon is a very small number, but it'll happen eventually. We don't care how long it takes. So then the question is what is the centripetal acceleration? Well, when the child is a distance r from the center, so that maybe they're halfway, maybe they're 3/4 of the way, whatever, or from the center, the centripetal acceleration, well, it's just, remember in terms of angular velocity, it's just r omega squared. In this case, it would just be r times omega of r squared. And the reason why omega here is a function of r is because we know that the merry-go-round is going to speed up as the child gets closer. So we can't use the same omega the whole time because omega is increasing as the child gets closer and closer. So we have to let it be a function of r in this case. And we're going to figure out what that function is using angular momentum conservation. So using angular momentum conservation, we have that the initial angular momentum is m capital R squared omega naught squared, or omega naught, and that should be equal to the angular momentum at any point when the child is walking. So in particular, that would be m, the angular momentum at some distance r would be m little r squared times omega of r. That would be the angular momentum at some distance r away from the center. And so we can solve the system when we get that omega of r is r squared over little r squared times omega naught. So this tells us how omega changes with distance as the child walks in. Great, okay. So then we can actually write what the centripetal acceleration is. It's just capital R squared over little r cubed times omega naught squared. So omega naught's a constant, r is a constant. So now we actually just have a function that depends only on r, which is excellent. So the static frictional force then is just, it's also a function of distance. It's mass times the centripetal acceleration plus epsilon. So it's m r to the fourth omega naught squared divided by little r cubed plus epsilon. Epsilon is just a little tiny bit. Now, note that the static frictional force points towards the center of the merry-go-round. It has to, because the object, or because the child is moving in very, very slowly shrinking circles. And the displacement vector also points in that direction. So in that case, the static frictional force is parallel to the displacement vector. And we're looking at infinitesimal displacement vectors, so that is certainly true. And so f sub s dot dl is just f sub s, the magnitude, times dl. So dl is moving from it's a path that goes from the outside edge of the circle to the center. So it's in the opposite direction of a vector of the path that goes from the center outwards. So this is just negative f sub s dr, where r is the variable, it's the coordinate that increases as you move away from the center. So now we can put it all together. Putting it all together, we can actually find the work done. We get that the work done as the child goes from radius r to radius r over 2 is equal to an integral of the work. It's from r to r over 2 of negative f of s, or f sub s of r dr. And now we can just plug things in. So we already know what that is. We can plug it in, do an integral. I will spare you the details. But what we end up with is 3/2 mr squared omega naught squared plus 1/2 epsilon r. And because epsilon could have been any tiny number, we're just going to take the limit as it goes to 0. And so what we're left with is that the work done, this is the smallest amount of work done, by the way. You could have more work done, and that would mean that the child is actually accelerating at a depreciable rate towards the center, but this is the minimum amount of work done, is just 3/2 mr squared omega naught squared, which is equal to the change in kinetic energy, which is good. Checks out. The change in kinetic energy that we got from the angular momentum conservation is precisely what we get from taking a closer look, looking at the actual static friction force involved on the child, and then computing the work done that way. It was a lot of work just to show that the work energy theorem is consistent. Sorry, the work energy theorem, but it's a good check. All right, so we got about halfway through. Yeah, about halfway through. Okay, so that's fine. We will end here and pick up next time. So